Hello, Thomas. It's Friday again.
Hey, Luca. So, what's up this week?
Yeah, this week I was at ECCV, European Conference of Computer Vision. It was a lot of fun. We had a booth there, and you were missing, but it's going to be the last one you miss, apparently.
Yeah, so I can walk again, at least a bit, and I'll be training for GTC, which had a deadline yesterday, right?
Yeah.
Make it
Apparently,
so.
we made it. Hopefully, we make it, to be
Yeah,
selected for a talk, and
that would
even
be
if not, we'll be there.
awesome.
Yeah. And then, we were chatting before. Getting into Milan is really random. You get to, no matter what time you leave, you get there at 10. So I try to leave at 8, 7, 8:30, because ECCV was in Milan. It was raining, it was miserable, but the conference was really nice. So that paid off. A lot of people interested in coming to the booth and interested in Thunder, actually. Quite a few people interested in how do I make it easier to deploy to the edge. We can't right now with Thunder, but we have all the ops. We could write a transform to transforms into something else, also some optimizations on the CPU. So there's so much to do when you have a trace that you can process, and so I try to kind of learn some of the people I was talking to about coming in, opening issues, and see what they need and so on. So that's exciting.
Yeah,
So where do we leave it off last week? So last week we said, okay, let's take LitGPT and Liger, which is a project from a team at LinkedIn that has optimized kernels for training, Trident kernels specifically. And we selected an activation function, SWIGLU, and wrote a fusion transform for it by fusing CLU and another operation right after. That was like composing the SWIGLU activation function. And we showed how you can just run it, and it was actually faster the moment we had the Trident kernel plus all the other executors.
right.
That was great. But now we want to do more. So Liger is a library that has a bunch of kernels. And so what happens if you want to
Yeah.
use more of them?
Let's look at the library a bit to see what's
Yeah.
going
Let
on.
me share my screen. Let me share my screen. So awesome. So do you see my screen? This is the Liger project. We can look around a little bit. So again, as I said, it's from people at LinkedIn. If you look into source Liger, you see ops, and there's a bunch of ops that we can use to further optimize. And we can see cross entropy, fuse linear cross entropy. So cross entropy is something that is used usually during train, right? It's a loss function that you use, and it's used to train language models. And why
Anything with classification.
anything exactly? But in language models, it's used, of course.
Yeah.
Anything with classification, that's right. And then you have a linear cross entropy fusion. Why would you want to fuse linear, which I suppose comes from the model itself, and then cross entropy which is a loss? Why do we want to fuse these two?
Right. So what happens is that the final output, of course, of all these models, the large language models, is an index into the vocabulary. So we have as many categories as the vocabulary size is. So this is thousands of categories, tens of thousands of categories, and so if you look at the cross entropy loss, the only thing that gets scored is the score of the category that is actually the target. So only the good ones get pushed up, if you want, and and by the implicit softmax, all the others will be pushed down. And so, because we only need this one entry of these many categories, it's much more efficient if we can just have the final entry and not compute all the other things that we're going to discard next.
Yeah, exactly. Because the softmax across all these words in the, well, this is not there, like the vocabulary goes across tokens. And so we need to predict the next token. Here I'm presenting pasta as a word. Maybe pasta is actually tokenized together. Then that's a good chance that it is. So don't take it as like a literal thing, but each of these things will have a different kind of weight that you can convert into a probability, right? So we'll have probabilities that are like spiking across the whole vocabulary of, well, I think vocabulary can be tens of thousands of these or even hundreds of thousands of these in some of the latest models. And then, of course, if we have to compute cross entropy across all of them, then it will be a large thing. And then we need to materialize them all in the middle, right? Between outputting these and computing the cross entropy. While we can just find out what you just said, the ones that if I'm talking about food, will be the softmax will kind of amplify and will squash down all the others. So maybe car will be 0.0000 something, right, and pasta will be higher.
Yeah, so strictly speaking, I think you do compute them all, but you don't materialize them. You don't write them into the memory, right?
Exactly, because you have a linear layer that will produce this long list of things, and then you compute the cross entropy.
Well, you first compute the softmax and then the negative likelihood, and then and you still need to compute the softmax, but only one output of it.
Yeah, exactly. And so in the end, you want to avoid materializing this, and materializing always means there's you store something back in memory, and that is something that if you can avoid, then you want to avoid it. So going back to our thing here, this is the code, the Triton code that does it.
Yeah,
and
maybe we should also add that this is kind of we've talked a lot about compilers and what they can do, and that they can fuse things, and they will be able to fuse things where they have recipes. But so this here, fusing the linear plus the cross entropy, is something that typically a compiler does not do on its own initiative. And so it's really great that the Liger team wrote a kernel for it. And to my mind, this is like the most valuable of the kernels, because it is something that is usually not generated automatically, where for the kernel we had last time, for the Swiglu one, the NVFuser, for example, will do a good job too.
Exactly.
Also, if you're interested into programming Triton, I mean, we had this example where we walked through it, but so here's an entire repository of them, right?
Yeah, exactly. It's so good to see, because the team spent a lot of time kind of so making sure that these things were written properly and optimized. So it's kind of a reference for that. And so if we go back into the Liger project, we also can see that there's a bunch of examples, or a few of them. One is Hugging Face. In fact, what we already mentioned the last time, one way of using these kernels is to have one-to-one mapping between one specific implementation of the models, and have a layer that replaces, or a submodule, an NN submodule that you can just go there and replace. So you can monkey patch things. So you initialize your Hugging Face model, for example. You get into the model with a dot, model dot whatever blocks, and then at some point you assign it to something new. And actually, we can take a look in Liger. Where is the monkey patching transformers here? Okay, and so monkey patch will
fairly modularized. And
yeah.
So,
you can see here, right? Sorry, yeah. It's a bit small, but let's say, okay, I'm importing modeling Llama, and then I'm getting into the things, and conveniently, Liger's sweet glue MLP, it's exactly what is needed to fit into Llama MLP. But in general, this operation will be very easy, right? And this is why we can take a model, put it in canonical form, and use transforms to actually map the implementation that you have that you may not even own because it may be your customers or another team generated that implementation. And a set of optimized kernels that can come from a library or multiple libraries that you want to apply. So you need to kind of transform your computation that results from your particular model implementation into something that is compatible with whatever optimized form of the operations you have. So I thought this was kind of important to look at. And in the examples here, you also have something called Lightning, which is, well, looks like we are involved here. And what is that thing?
Right.
This is, yep.
So this is PyTorch Lightning, obviously, which is a cool framework to get the all the engineering, the automatic multi-precision, and all these things for you, the distributed. And so people use it a lot. It's a lot more popular than Thunder, at least for now.
Yeah.
But so that's the Lightning part. And here you see the trainer being invoked, right?
Yeah, exactly. So PyTorch Lightning is becoming one of the standard ways of using PyTorch in organizations. And we are seeing it from the downloads. We have like 150 million downloads totally, and about like 8-9 million downloads per month. It means that people are relying on the Lightning trainer to basically take a lot of the engineering details on how you scale models across machines, across GPUs, how you use strategies or callbacks, for example, to save checkpoints, to log properly. And if you let the trainer take all these things away from you, it's not because we want to bottle things up so you don't have control over them. You can still have control over them, but you avoid making mistakes because it's so easy to put something in there that will basically trash your performance in production systems. So instead of like figuring everything out, we kind of take care of a bunch of things. And one more thing that it's important to mention is that PyTorch Lightning doesn't require you to write models in a different way compared to PyTorch. It's still pure PyTorch. We don't wrap a la Keras, for example. And so you can see here in the configure model, we just basically instantiate the Hugging Face model, the Hugging Face version, the patched Liger version of the Hugging Face model, the monkey patch one. And then you say, okay, my forward is just self.model. And what PyTorch Lightning requires to do is you take your training code and you break it up and organize it into lifecycle hooks, essentially. So training step here will compute outputs from the model and then access the dot loss, which is common in Hugging Face land to call the forward and you get the loss as a part of the output. And then, well, here you log the dictionary to do distributed logging. this is something we take care of in PyTorch Lightning, and then you return the loss to be consumed by the optimizers. And the optimizer are defined in configure optimizer. So instead of writing one monolithic function, you break it up into the things, and then the trainer will know which one to call in which lifecycle moment. Anyway, and now for PyTorch Lightning, I strongly suggest you check it out because it's actually powering a lot of the large scale trainings, like from Stable Diffusion. That's all based on that. All the NEMO models are based on that. And a lot of organizations are using it. But what do we want to do today? Well, the Liger example, we said, uses Hugging Face within and then PyTorch Lightning. Now, what we want to do is say, okay, now we don't want to use the Hugging Face model, but we want to use LitGPT because you don't own, like, as we said, we have the use case where you have an implementation and you have a set of kernels that was not thought for that particular implementation. So how do you bridge that gap? And we'll show you how to bridge the gap using Thunder to transform the computation so that you can now apply those kernels. All right, so we said LitGPT, since I have the browser open here, this is LitGPT, and we're looking at 3 additional operations, right, today. One is, well, we did Swigglue already. We're doing rope, we're doing cross entropy, and we're doing RMS norm.
Yes, if we want to. I mean, but if we want to. Norm maybe is the least interesting, but
yeah, for sure. So let's look at one of the nice things about LitGPT, and we've always said it, is that the whole implementation is contained in this model.py. Rope is, so what is rope in a language model? Rope is the way where is it? Sorry, the rope cache.
Yep.
Here, there's a function here that computes this rope thing, this rope cache. What is rope? Is a way for the model to figure out where in the context am I at the beginning, am I at the end? Are these two words far or close to each other?
So the funny part, if you want, with transformers, obviously you have the embedding vectors, and then you encode the positions. But the funny thing about transformers, and this goes way back to BERT and the Attention is All You Need paper, is they tried like concatenating the information for the position or just adding it to the thing. And both worked well, and so they decided that they would add it. And now rope is a bit of a twist where you encode the positions via sine and cosine. And this is pre-computed, the sine and cosine. And then you rotate the vectors between one position and the other. And the rotation like gives you an indication of the position, and similar to the cosine loss, which you use for like image retrieval, you have that the rotations, if you have like the same distance, it's like a relative positional encoding, because if you have the same distance, the rotations will be the same relative to each other. And so
exactly. So two things that are like not too far, no matter where in the sentence you are, will basically projecting to each other closely, and things that are very far will basically project the other way. This works well in practice. It's not something that I would have said it would work because you're kind of messing with the embeddings, right? You get a nice embedding, and then now you like apply a weird function to it. In the 2000s, I did a lot of medical imaging. And when you do MR, when you get into an MR scanner, basically the MR scanner does something similar because it encodes the water content in your body or the magnetic properties in your body as a Fourier transform. So there's a literal antenna that basically acquires the Fourier transform or whatever you're made of. And so this thing kind of got a bit familiar with that, although it's not exactly that. It's kind of reminiscent to that.
I mean, so one thing is that the things, the transforms you have in MRT, the thing that is recorded is like the mathematician says, an ill-posed problem for the to recover the data, because if you wiggle just a little bit at the measurements, you get totally different data, and so the noise in the measurements really is a problem. But so here, I think you have the effect that it's like really nifty that you have the in the end, it's the scalar product between two things is the thing that is important.
Yeah.
That's why it's called dot product attention, right? So the dot product is important, and so this manipulates directly the dot product between two things. If you have like the same token one thing away, it will give you the angle precisely, and so this is kind of
that's a good interpretation. Yeah, that's a very good interpretation. We do the products, which are basically weighted sums of things, and this way of applying transformations as the most possible direct effect on that dot product. So yeah, that's great. All right. So anyway, the rope, you pre-compute a lot of sines and cosines. You have a cache that you can then apply to your embeddings, and then that is good. But what if you want to optimize that part and have the application of the rope be an optimized fused kernel? Because we saw that, like here, for example, apply rope here. Where is it? Here has a bunch of operations, and so for each one of these operations, you need to go back and forth. Again, it's better to fuse rather than to go back and forth. All right, I'll stop here, and now it's your turn. Yeah.
Yeah, if you look at that, there's a torch cat which concatenates two tensors. But so this is something that a compiler can optimize very well, because it can just pre-allocate the buffer and tell the operations before it, yeah, you write your result in here. And this is precisely what people do. And then there's a few pointwise operations like before and after. Before you have the minus x2, and afterwards you have this rope is the product of the cosine and the rotated times the sine.
Yeah, what you said in terms of cat makes it also clear why it is hard to do this kind of optimizations with a purely eager framework, right? You need the context of why you're doing the cat, and like what's entering in the cat, and how you're going to use the cat, the result of the cat. And so you need a full graph or the vicinity of all these operations to reason about it. All right, I think that's fine. For the cross entropy, we made a minor modification to the model to take the cross entropy actual operation that is in the pre-train.py or fine-tune.py, because it kind of pertains more to the loss. So it's outside in LitGPT, it's outside the model definition. We brought it in. In the future, we'll like acquire the whole step. Right now, we generally acquire the model so that we made this modification just in case you're kind of trying to follow through LitGPT, but we'll publish all this stuff and upstream it to the repositories. All right, so I'll pass you the ball to show how the sausage is made in this case. We put a bit of context because we're going through a bit of things. So I hope now things will be clearer.
Yeah, so let me try to share the right window.
Yep.
So here we have, I took the studio that I prepared, and I added, or the notebook in the studio, and I updated Liger and Thunder to have the newest and greatest. But so one thing we did, we defined the kernel here, and then we had various things. So last time we looked at the Swiglu. Another kernel here is the rope forward. And so the particular thing about the rope forward is that in contrast to the apply rope that Luca just showed you, this would be called twice in the GPT, once for Q and once for K. But the Liger colleagues, they have one forward function that does both of them. And so this is great. And we can define our kernel or define our meta function, which will, for technical reasons, it seems to return cosine and sine. But so the Q and the K is basically rotated and then returned. And we can register this operator with the meta and with the call to the Liger kernel itself. And we have a backward kernel, and we can define the grad transform. And you remember we first call the forward, and then we get the gradients of the outputs, and then call the backward kernel, and then we put the gradients in order to tell Thunder how to connect the various things. But now the thing is that we again need to transform. When we trace through LitGPT, what will happen is that we have two invocations of apply rope, and we need to transform this to one. And to make our lives easy, I did a very lame thing here. I just defined a little apply rope meta that now takes only one of them. So X could be Q or K. And I registered an operator that has this apply rope as its implementation, and this little trivial meta function as the meta. And now Thunder will record apply rope as one symbol in the trace. And this is very valuable because now our rope transform goes like all the transforms go. And so
so in a way we were lucky that there was a function called apply rope in the LitGPT repo, right?
Yeah, that was pretty lucky.
A lucky coincidence.
It's the good taste. I mean, I always try to tell people, if you do modules, if you define custom modules and you're building something that is built for reuse, like LitGPT is, then it's always good to have this functional interface that PyTorch also does, like a torch-in functional. And so this is one of the things where we got lucky with this. And actually, one of the things I last put into LitGPT was to have a batched index copy as a separate function in order to process batches of inputs also in inference. But yeah, so this is as it is. So what we do is we find one bound symbol that is LitGPT apply rope, and then we're looking for the next one, and we need to make sure that we're not using the output in between. So we can actually fuse the two, and we don't accidentally fuse one half of rope from one block and the other from the next block, because that doesn't work with the data flow.
Oh yeah, for sure. Because as we have many blocks of this, so we need to take one and the other, fuse them together. Yeah. In the meantime, we need to check that no one is using the output of the first. Otherwise, when we fuse, somebody will be, left out of the party.
Yeah, before in Swiglu, we wanted to fuse two consecutive operations. So we could say, find me the consumer of this operation, but we can't here. So we're searching for it manually. Obviously, Luca and I, we're always chatting after the episode. What do we like? Where would we like a better user interface? And we will have a very nice pattern matching thing that will allow us to do this much more elegantly than spelling out the transformation eventually. But so here we then replace like the two, we mark one for skipping, and then we replace our call to the rope with the Liger rope call. And so this is how we get the rope. And of course, we can then test it. And I made a little test here. I'm not going to run it, but I made a little test that just takes a LitGPT model. And so we can do all the operations. So RMS norm is, again, very straightforward because it maps to there's a one-to-one correspondence between the RMS norm function. Well, actually not, but I made LitGPT use this. There should be a one-to-one correspondence. And then there is this fuse cross entropy and linear, and this kind of works exactly the same as the fusion for the swig loop, where we
or the fusion for the linear and reloop, right? Yeah, it's actually even closer to that one, right?
Yeah, right. We find the linear, and then we check has it only one consumer, and is the consumer the cross entropy, and then we can repeat it. And so,
same old.
Yeah, if we did that, we can actually, and I did this here, I copy pasted the entire Liger example. And because I just love the new Llama 3.2 1 billion as a demo model, I took that and then I modified the LitGPT model to include the cross entropy. So it starts out, and I'm using a little trick here on the attention mask because when you batch things of different lengths, as the example does, you need to play tricks with the attention mask so it adds up properly. And then
maybe we can touch upon this in some of the future episodes, because there's so much you can like get blocked on when you do these things.
And so here at the end, we have this language model head, which does all the predictions for the different elements of the vocabulary. And then here's the cross entropy, right. It returns the loss. And so this now is a thing that is more or less faithful. It has been like made to accept more or less the same inputs as the model that Liger came with, adapted from Hugging Face. And so we can now instantiate the model here and load it state dict in order to do fine-tuning. And all we need to do here is thunderjit the thing with our new LigerX executor. And then we need to remember to also include the transforms. And when we have that, we're basically all set. And of course, here with the executor and the transforms, this is also something we want to make easy eventually for you with recipes, and that will be exciting. But then if you have this, you can basically just run the thing in the trainer. And I did this for you, and I greatly reduced the number of batches we pass through here. If we look at it the first time around, we're terribly slow. So 0.03 iterations per second. I need to compute that. That is about 33 seconds per iteration.
Yeah, not exactly a speed up.
Yeah, that's not a speed up. And so what happens here is that Thunder, in its default configuration, it recomputes, it reinterprets the entire model whenever shapes change, the input shapes in particular. And so this is kind of slow, and you would typically pad to like reasonable multiples of powers of 2 or something in order to avoid this recomputation. But we can see if I do a second epoch, obviously the lengths in the second epoch are not guaranteed if you reshuffle your data set. But if you have the same batches, it will be more or less the same. And then things get really fast here. So we get 7 iterations per second.
Oh, wow.
I didn't try like what we get without Thunder. We can just leave out the JIT call, right, in order to figure that out. And this has not been rehearsed, nor did I ask Luca if he wants to do it. So it's risky again.
Yeah, it may, we may get,
Yeah, I mean,
any number now.
We will, so what happened here? It didn't finish yet? Okay.
Yeah, it didn't finish yet.
So now it stopped. And now it's doing the upper thing. And now this is without Thunder. And so you see Lightning initializing, detecting the hardware. And if I forget to move things to CUDA and Lightning doesn't do it for me, then it will yell at me, which is good. And so we have the data pre-processing, and here we get like also 7 point something iterations. So more speed up needed in order to really reach the maximum performance. But so we did have that we could run the model, and it would. And next time we will see that it actually takes all the optimizations, and then we can see the speed up. Probably it also works better when you tune the other parameters and make sure that you have a more continuous use of the GPU during training.
Yeah, most of the times, doing toy runs informs you up to a point of where your performance will be. It's also possible that the kernels themselves were optimized in a certain regime. So there's a lot to explore here. The goal for today was to make you give you an idea, and I think it was nice because we showed something that we knew already how to do more or less before. With the transformer, they were a very similar nature. So we went through rope that was one function call in transformer. So there was one function call applying rope to Q and K, Q and B on the on Liger, because it followed after transformer. In LitGPT, we have two separate calls for the two tensors, and we understood how to kind of do one of them. And then for the other kernels, we adopted very, very similar patterns than the ones we applied to even linear and relo in the first series of fusions we made. I think the next time would be interesting to, now we want performance, and now we have the leverage, right? So we can also show how to profile things and say, okay, where are things slow or still slow, and see how we can actually tune it so that it's as fast as possible. So anyway, that was great.
Yeah.
Thanks a lot.
Luca, you have Thomas. A good weekend, and also everyone out there.
Yeah. And try things out. We'll publish the material and open issues in Thunder. Coming up is also recipes that Thomas mentioned. And so that you don't have to know all the things that we are saying in the episodes in order to apply the optimizations. We're thinking about ways to package up a set of optimization for a set of models, so you can just apply them, or different optimizations, because, depending on the hardware you are and the kind of data you have, how much things change across batches and so on, you may want to hit a different set of executors, different set of kernels and transforms and so on. And so we'll learn how to do all that. And then, till the next time.
That will be awesome. So, see you.
Thank you, Thomas.